Suppose the price of a good falls. Consumers usually buy more of that good. But economists immediately ask a deeper question. How much of this increase occurs because the good became relatively cheaper? And how much occurs because the consumer has effectively become richer? The answer leads to one of the most important results in microeconomic theory: the Slutsky decomposition. By the end of this lesson, we will prove mathematically and graphically that price effect equals substitution effect plus income effect. We will derive Marshallian demand, derive Hicksian demand, construct compensated budget lines, and finally derive the Slutsky equation itself. We begin with utility maximization. Suppose a consumer chooses quantities of two goods, X and Y. The objective is to maximize utility subject to a budget constraint. The Lagrangian becomes: the first order conditions are dividing one equation by the other gives. Since marginal rate of substitution equals the ratio of marginal utilities, this is the familiar tang-in-C condition. Consumer equilibrium occurs where the highest attainable indifference curve touches the budget line. Let the utility function be of the Cobb-Douglas form. Income is 100 units of currency. Initially, the prices of goods X and Y are 10 and 5, respectively. Our goal is to determine the consumer's optimal consumption bundle. For the Cobb-Douglas utility function, the optimal quantities are given by the Marshallian demand functions. Substituting the given values, the consumer purchases 5 units of good X and 10 units of good Y. This is the consumer's initial equilibrium. Let us call this point A. Now suppose the price of good X falls from 10 to 5. Income remains unchanged. The budget line rotates outward. The consumer can now afford to purchase more of good X. Using the same Marshallian demand function, we find that the equilibrium quantity of X increases from 5 units to 10 units. The equilibrium quantity of Y remains at 10 units. The new equilibrium is point C. Consumption of good X has increased from 5 units to 10 units. The total increase is 10 minus 5, which equals 5 units. This is called the total price effect. But this total effect is actually made up of two separate forces. Imagine we could perform an experiment. We allow prices to change, but we somehow prevent the consumer from becoming richer. Then any behavioral change must come purely from relative price changes. This pure response is called the substitution effect. After measuring that effect, we allow purchasing power to adjust. The remaining movement becomes the income effect. This is the basic logic behind Hicks and Slutsky decompositions. Sir John Hicks proposed holding utility constant. The consumer must remain on the original indifference curve. Only relative prices are allowed to change. To achieve this, we construct a compensated budget line tangent to the original utility level. Movement from A to B is the Hicksian substitution effect. Movement from B to C is the income effect. Movement from A to C is the total price effect.
To understand substitution effect formally, we derive Hicksian demand. Instead of maximizing utility, we minimize expenditure. Notice the reversal. Marshallian demand solves utility maximization. Hicksian demand solves expenditure minimization. The resulting demand function is called compensated demand. For the Cobb-Douglas utility function, we begin with the utility constraint. Squaring both sides gives the equivalent constraint. Next, solve the constraint for good y. Then substitute this expression into the expenditure function. Differentiate the expenditure function with respect to good x. Set the derivative equal to 0 and solve for good x. This gives the Hicksian demand function for good x. Notice something important. Income no longer appears in the demand function. Hicksian demand depends only on the target utility level and prices. That is exactly why it captures pure substitution behavior. Marshallian demand depends on income. Hicksian demand depends on utility. Marshallian demand contains both substitution and income effects. Hicksian demand isolates substitution effects. This distinction is the heart of modern demand theory. Eugen Slutsky proposed a different compensation rule. Instead of holding utility constant, he held purchasing power constant. Specifically, he adjusted income so the original consumption bundle remained affordable after the price change. This creates a compensated budget line passing through the original bundle. The resulting substitution effect is called the Slutsky substitution effect. Now we reach the central result. The total response of demand to a price change can be decomposed into two parts. Using calculus, differentiate with respect to price. After a series of substitutions involving compensated demand, economists obtain. This is the Slutsky equation. The left-hand side measures the total price effect. The first term on the right-hand side measures the pure substitution effect. The second term measures the income effect. Therefore, price effect equals substitution effect plus income effect.
Let us now summarize the entire analysis. We began with a Cobb-Douglas utility function and an income of 100 units of currency. Using the Marshallian demand functions, we found the initial equilibrium at point A, where the consumer purchases 5 units of good X and 10 units of good Y. Next, the price of good X fell from 10 to 5, while income and the price of good Y remained unchanged. Applying the Marshallian demand functions again gave the new equilibrium at point C, where the consumer purchases 10 units of good X and 10 units of good Y. To isolate the substitution effect, we held utility constant and used the Hicksian demand functions. This gave the compensated equilibrium at point B, where the consumer purchases approximately 7.071 units of both goods. The expenditure required to achieve the original level of utility at the new prices is approximately 70.71 units of currency. We can now decompose the total change in the demand for good X. The total price effect is the movement from point A to point C. Numerically, this equals 10 minus 5, or 5 units. The substitution effect is the movement from point A to point B. Numerically, this equals 7.071 minus 5, or approximately 2.071 units. The income effect is the movement from point B to point C. Numerically, this equals 10 minus 7.071, or approximately 2.929 units. Adding the substitution effect and the income effect gives 2.071 plus 2.929, which equals 5. This exactly matches the total price effect. Therefore, we have verified both graphically and numerically that the total price effect is equal to the substitution effect plus the income effect. For normal goods, income effect reinforces substitution effect. Demand rises strongly when price falls. For inferior goods, income effect works against substitution effect. Demand still usually rises, but by a smaller amount. For Giffen goods, the negative income effect can become so strong that it overwhelms substitution effect. In that rare case, demand rises when price rises.